So when we last left off, we discussed many methods to engage alcohols in reactions. What we're next going to talk about is this idea of protecting and masking alcohol functionalities to prevent undesired reactions and to allow us to control the reactivity of alcohols. The protection and protecting groups allow us to control the chemoselectivity and reactivity, and it allows us to ensure that our reactions are selective for the desired products. So hydroxyl groups can easily transfer their proton to a basic reagent. For example, if you have an alcohol and an alkyl halide and you try to make a Grignard, this reaction will fail miserably. The carbon-magnesium bond is incompatible with the acidic protons in the same molecule. So one way to get around this is we can convert the hydroxyl group to a removable functional group without an acidic proton. So protection involves three principal steps. You introduce a protecting group to block the interfering reaction. You carry out the desired reaction. And in the final step, you remove the protecting group. So, although this uses up a lot of reaction steps, this is a wonderful way to enforce chemoselectivity. Any questions so far on why we care about protecting groups? Any questions so far on the purpose behind protecting groups? Okay, so let's talk about typical protecting groups and how the protecting groups are installed. So let's talk about methods to protect alcohols. The most common protecting group is the trimethylsilol or TMS protecting group, which is installed by reaction of an alcohol with chlorotrimethylsilane in the presence of base. So the base helps form the alkoxide ion and removes any acidic byproducts generated. So in the first step, our base removes a proton, and then our alcohol attacks our electrophilic silicon atom, kicking out our leaving group. This generates a trimethylsilol ether. So our alcohol functionality is masked and protected as a trimethylsilol ether. This silol ether can then be cleaved with acid or with a fluoride ion source such as TBAF to regenerate our alcohol. So protecting an alcohol is a relatively straightforward process. Treatment with a base, such as in this case triethylamine and trimethylsilol chloride, gives us our trimethylsilol ether. So this alcohol is protected from further reactions. So
we have a question.
Yes, please go ahead.
Is the base the chlorotrimethylsilane?
No, so the chlorotrimethylsilane is our electrophile.
Oh, okay.
And it's used to install the trimethylsilane protecting group. The base in this case is triethylamine, which is our basic functionality necessary to deprotonate our alcohol and to remove any acidic protons generated as a byproduct from this reaction. Does that make sense?
Yeah, okay. Thank you.
Mm-hmm. So what is the use of a protecting group? What are some key important uses of a protecting group? So let's suppose that you have two functionalities in your molecule. Let's suppose you have an aldehyde and an alcohol. And you want to selectively oxidize your aldehyde. Well, this alcohol is going to get in the way of that. So you can treat this entire molecule with TMS chloride and triethylamine. You generate the trimethylsilyl ether of your alcohol. And then from there, you can oxidize your aldehyde. And you can oxidize your aldehyde up. Under basic conditions. And then from there, what we notice is because our alcohol is protected, we will only react our unprotected aldehyde. So this gives us a wonderful method to enforce chemoselectivity. And in the end, we can just remove our protecting group at the end of this synthetic sequence. You can contrast this with what would occur if we try to use an unprotected alcohol in this process. So if we try to oxidize under basic conditions, we would end up oxidizing our alcohol functionality as well. So as you notice, depending on whether or not we have a protecting group in place, that determines whether or not we engage our alcohol in the oxidation reaction in this case. Does that make sense? Does this idea, and does everyone see the role of protecting groups in this case? Any questions from here? If not, let's keep going then, and let's discuss a typical sequence to generate, for example, a Grignard from a fragment that contains an alcohol. So obviously this alcohol is incompatible with a Grignard reagent. So to get around this, we're going to protect our alcohol as a chloro-trimethylsilyl ether, or in this case, a trimethylsilyl ether. We're protecting our alcohol with chloro-trimethylsilane. So that generates our trimethylsilyl ether. And then from there, we can generate and efficiently generate our Grignard reagent. The Grignard reagent is compatible with ethers, while it would not be compatible with an unprotected alcohol. We can then perform a Grignard reaction with an aldehyde or another electrophile. And then for our last step, we remove our protecting group under acidic conditions, or you can use TBAF, which is tetrabutyl ammonium fluoride. Which is a fluoride ion equivalent. So to talk a little bit about the mechanisms for removing protecting groups, let's just talk about what happens if you have your typical trimethylsilyl protecting group and you are trying to remove this protecting group. And let's first look at what happens under acidic conditions. So under acidic conditions, the first thing that's going to happen is we're going to protonate this trimethylsilyl ether oxygen. So we're slowly generating a more activated leaving group. And then from there, water is going to attack and we're going to kick out our leaving group. So that in turn gives us our free alcohol and trimethylsilyl alcohol, which is easily removed with a water rinse. Does this acid-catalyzed mechanism make sense for how we deprotect a trimethylsilol group under acidic conditions? Does this mechanism make sense to everyone? So this is the acidic deprotection mechanism. Any questions so far? Okay, now let's look at the basic conditions for deprotecting a trimethylsilol protecting group. So under basic conditions, deprotection only really works efficiently with tetrabutyl ammonium fluoride or another fluoride source. In this case, the deprotection follows closer to that of an SN2 reaction, where fluoride attacks our silicon atom and we kick out our leaving group. This in turn generates an alkoxide ion that can then be used for further reactions. So the reason why the basic deprotection conditions using tetrabutyl ammonium fluoride are so useful is that they allow you to very selectively generate an anion that you can use for further reactions. So depending on what you want to do with your deprotection, one benefit as well for these protecting groups is they allow you to selectively generate ions and anions through this deprotection step. So in many cases, we'll see examples of this later on when we look at enolate chemistry and enamine chemistry, where the protecting group is removed, we generate an ion, and then we can use that anion for further reaction. So we can alkylate this anion, we can use it as a base for intramolecular proton transfer. There are a lot of things we can do once we have this anion generated. Does everyone understand the mechanism for acidic and basic deprotection of our trimethylsilol group? Do these mechanisms make sense to everyone? Does the removal of the trimethylsilol group, once you quench the solution with acid, you typically retain the silol fluoride because the silicon fluorine bond is very strong. This is one of the driving forces for why this deprotection with a fluoride ion occurs so readily. And that's because the silicon fluoride bond is uniquely stable. Does that make sense? Perfect, perfect. So let's keep going, and I'd like us to draw the product from each step in the following reaction sequence, and I'd like us to draw a mechanism for each step. So we have an alcohol, and we treat it with chlorotrimethylsilane and pyridine. And then we make and we isolate this product A. So what's occurring in the first step? What's occurring in this first step here? What are these conditions trying to accomplish? What's going to happen under these conditions? alcohol protection. Yep. So our alcohol will attack our electrophilic silicon atom and displace chlorine, or more specifically, displace chloride. That in turn generates our trimethylsilol ether. And pyridine plays a really important role in this process in that it's serving as our weak base that will pull off the proton and give us our neutral product. Note, just like making a tosylate, protecting an alcohol as a silyl ether does not change that alcohol's stereochemistry. Does this make sense to everyone so far? Does everyone see how the first step we're just doing a textbook alcohol protection as noted by many students in the chat? Okay, so what happens next? Because alcohol protection, the reaction occurs at the oxygen center. Because the reaction occurs at the oxygen center, the stereochemistry at our carbon center does not change. So protection of an alcohol occurs with no change in the alcohol stereochemistry. Just like making a tosylate. Okay, so we have our protected silyl ether, and now we're treating it with ethyl magnesium bromide and THF, and then we have some quench steps. So what's going to happen when we treat this molecule with ethyl magnesium bromide? What is going to happen? A Grignard reaction, right? And where will the Grignard add? Well, what is our electrophile in this case? What is our electrophile for this Grignard reaction? The ketone carbon, exactly right. So ethyl magnesium bromide is going to attack our electrophilic ketone. So at the end of our first step in this sequence, we'll get addition into our ketone. And then in our second step, when we treat with H3O+, it's likely that during the acidic quench step, if you use a strong enough acid, you would be able to also deprotect this silyl protecting group. So the TBAF step is somewhat unnecessary. I just added it to clearly indicate that we're removing our silyl protecting group. So in the end, we would be able to isolate the Grignard addition product. And at this stereocenter, we would expect to see a mixture of stereoisomers. Just because the Grignard can attack from the top or bottom face. So, does everyone understand why we need to use a protecting group for this sequence? And does everyone understand what's happening in this two-step reaction sequence? Does this make sense to everyone? Any questions on this example? Any questions on what each of these reaction conditions are accomplishing? Okay, so to elaborate a little bit on why this protection sequence is necessary, if we tried to take our unprotected alcohol through this sequence, would we get the desired product? So if we took this substrate and we reacted it with ethyl magnesium bromide, would we get out the desired product that we're looking for? What does the class think? If we took this unprotected alcohol and reacted it with this Grignard, would we get the desired reaction? Would we get the same product as through the protection sequence? We have a lot of students typing no, the Grignard would be quenched by the alcohol. Exactly right. So the reason why we use a protecting group is to ensure we get the desired chemoselectivity and we avoid undesired side reactions. The Grignard reaction would not work unless our alcohol is protected. Does that idea make sense to everyone? Does this concept make sense? Perfect. So then let's keep going now. I just provided another page in case we needed more space. Okay, so after this example, let's talk about another reaction that can be used to protect alcohols, but also to make alcohol derivatives. And that is the preparation of esters from alcohols. So let me just get the Zoom set up so that way we can fully see. Okay, perfect. So carboxylic acids can be directly converted to esters if a strong acid is used. In many cases, the carboxylic acid is activated by first converting it to an acyl chloride or acid chloride using thionyl chloride. So in both cases, we're dealing with a textbook carbonyl substitution. I'm going to highlight some mechanisms here, and I'm going to highlight first the mechanism for generation of an acyl chloride using thionyl chloride. So if we treat a carboxylic acid with thionyl chloride, we're able to efficiently generate the acyl chloride. This is quite an informative mechanism to discuss because it highlights a central idea in carbonyl substitution. So our first step, our nucleophile, which is the carboxylic acid oxygen, is going to attack the electrophilic sulfur in thionyl chloride. From there, we're going to kick out a leaving group. So we have, in effect, in this process, generated a highly activated leaving group. Chloride then is going to attack our most electrophilic atom, and it'll attack the atom that would lead to a productive reaction. So we're going to attack our carboxylic acid carbonyl carbon. Now, What's really interesting here when we think about carbonyl substitution reactions is which leaving group is better, chloride or this highly stabilized anion? Which leaving group looks like a better leaving group? Which leaving group can readily stabilize a negative charge? What do we think? We can kick out chloride, sure, and that would be reversible. But we can also kick out this. We can also kick out this sulfonyl chloride, or this thionyl chloride derivative, and that would give us our desired acyl chloride. Let's start from our carboxylate under basic conditions. So this is an example of the basic conditions for carbonyl substitution. Does this idea of carbonyl substitution under basic conditions make sense? Our nucleophile attacks, we have a tetrahedral intermediate, it collapses down, we attack our carbonyl carbon, we make a tetrahedral intermediate, and that tetrahedral intermediate collapses. Does that idea make sense for basic conditions for carbonyl substitution? Any questions on this mechanism? This is a wonderful way to convert a carboxylic acid into a more activated acyl chloride, which is more reactive towards substitution and carbonyl substitution conditions. Does that make sense to everyone so far? Okay, so let's look next at the acidic conditions to prepare esters from alcohols. So under acidic conditions, we have to activate our carbonyl. We have to activate our carbonyl. So in the first step, we're going to protonate our carbonyl. This activates the carbonyl as an electrophile. Next, our nucleophile, such as water, will attack our electrophilic carbonyl carbon. From there, we have a tetrahedral intermediate. In order to set up our molecule to kick out water, we need to undergo a proton transfer, where a proton is removed from our added alcohol and water picks up a proton from the solvent. We now have water as a wonderful leaving group. So when we kick down and collapse our tetrahedral intermediate, we can kick out a great leaving group in the form of water. Finally, as our last cleanup step, we deprotonate our carbonyl oxygen, and that gives us our neutral product after trans-esterification. One thing I'd like you to note is this is an equilibrium process, and this is driven to completion using two main tricks. First, we use an excess of the alcohol, and two, we remove the water via drying or Dean Stark conditions. So these are two methods that we can use. You can either add a drying agent to your reaction. You can use a solvent system that azeotropes off the water, or you can use a formal Dean-Stark trap to capture the generated water to help drive this reaction to completion. Does this make sense to everyone? Does this mechanism make sense and how this equilibrium is forced to completion? By Le Chatelier's principle, if you use an excess of reactant, that drives the equilibrium towards the product. By the same notion, if we remove our byproduct water, that also drives the equilibrium towards the product and drives the reaction towards completion. Any questions on this reaction and these conditions? Okay, so let's keep going now and let's look at the application. Oops, sorry about that. Okay, so let's keep going and let's focus on the application of these acid-catalyzed trans-esterification reactions. So in this case, we have a carboxylic acid and an alcohol under acidic conditions. What product will we observe? And I'd like to have students draw a mechanism for this reaction. I'd like to see that students are comfortable drawing a step-by-step mechanism for trans-esterification of alcohols and for acylation of alcohols under acidic conditions. So let's take a few minutes to work on this example. And ideally, I'd like to have students share a mechanism on the class whiteboard, just so that way I can get a sense of how the students are approaching this mechanism, and so that way we can discuss this mechanism as a class. So would anyone like to volunteer drawing out the mechanism for this reaction? Or do we have any questions as we work through this mechanism? And really don't be shy to draw the mechanism on the class whiteboard, and there's plenty of space for multiple students to annotate. Or would anyone like to suggest the first step in this mechanism? So we're under acid-catalyzed conditions. So what's the first thing that's going to happen? Protonation, yeah. So under acidic conditions, the first step is we're going to protonate our carbonyl oxygen to activate our carbonyl oxygen. Okay, we now have a pretty reactive electrophilic carbonyl carbon. So what's going to happen next? What's going to happen next? So we have our alcohol, we have an activated electrophile. So what's going to happen then? Would anyone like to draw the next step or describe the next step for this mechanism? Yep, our alcohol is going to attack our carbonyl carbon. Yep, exactly right. Of course, these are equilibrium processes. Okay, now in order to activate water as a leaving group, what's the next step? What's the next step that's going to happen? So it's important that we draw this step as intermolecular rather than intra, because intermolecular proton transfers aren't favorable and aren't geometrically allowed in this case. So what's the next step? So how do we activate our alcohol? How do we activate and make water as a leaving group? Oh, yep, that's a typo. So what's the next step in this sequence? So how do we generate a more reactive activated leaving group? What's our next step? Yep, so we're going to have a proton transfer step. So water is going to shuttle a proton, and our solvent's going to serve to shuttle a proton. So first we're going to pull off a proton for the alcohol that added, and we'll donate a proton to activate and make water as a much more useful leaving group. So that in turn generates the following product. Again, all of these steps are equilibrium. Okay, so from here we have this tetrahedral intermediate, and what happens next? What happens next? Yep, water leaves as we collapse our tetrahedral intermediate to regenerate our carbonyl. So that in turn gives us the following protonated ester. And then for our last step, all we have to do is pull off our proton. There we go. And that generates our desired trans-esterification product. Perfect. Does this mechanism make sense to everyone? So this is a textbook method to both protect alcohols and to generate ester derivatives of alcohols. And in this case, we've showcased the acidic mechanism for trans-esterification. Any questions on this mechanism?
I have a question, Professor.
Yes, please go ahead.
How did you know it was acidic?
Because we're running this reaction in the presence of acid. the H3O plus tells us that we're
Yeah.
working under acidic conditions.
Oh, okay. Thank you.
Does that make sense?
Yes.
If we're under basic conditions, we would be dealing with the anion as our nucleophile. Does that make sense?
Okay. That makes sense. Thank you.
One other thing that I would like to comment is that carboxylic acids are typically unreactive or very slow to react under basic conditions, while they react readily under acid-catalyzed trans-esterification conditions. It has to do with the fact that because carboxylic acids have an acidic functional group, under basic conditions, carboxylic acids get deprotonated, and then they're very slow to react because the leaving group is O2 minus, and that's a terrible leaving group. Does that make sense? So typically, if you want to make ester from a carboxylic acid, you overwhelmingly will use acid-catalyzed trans-esterification conditions. Okay, any other questions on this example? If not, let's keep going then. Okay, so what we're going to talk about next are methods to generate ketones, carboxylic acids, and other oxidized derivatives from alcohols. So we can oxidize alcohols using a number of reagents such as permanganate, chromium trioxide, sodium dichromate. You generally need more selective, gentler reagents to stop the oxidation at the aldehyde, though it's easier to stop an oxidation at the aldehyde versus stopping a reduction at the aldehyde stage in general. So the way that I like to think of oxidation is loss of a hydride equivalent. So let's do some oxidation number counting. Let's do some oxidation number counting for some of these structures. So if we have a primary alcohol has an oxidation number of, so using our oxidation number counting method, so we have an oxidation number of 4 minus 5 or minus 1. To go to an aldehyde, we see an aldehyde has an oxidation number, in this case of plus 1. While a carboxylic acid has an oxidation number of, would anyone like to comment? What's the oxidation number of a carboxylic acid? Just to make sure we're on the same page. And just to make sure we're comfortable with this, what would the oxidation number of a carboxylic acid be? Plus 3, exactly right. Perfect. Now, as we notice, if we take a look at the hydrogens, as we notice, in each oxidation step, we lose a hydride equivalent. And correspondingly, our oxidation number changes by 2, right? So each hydride equivalent leads to an oxidation number change of 2. Does everyone see how each oxidation step is removing a hydride equivalent? How each oxidation step removes a hydride equivalent and our oxidation number becomes more positive as a result. Most oxidizing agents can be thought of as reagents that remove or abstract an equivalent of hydride. So, on that note, if we have, for example, a secondary alcohol and we subject it to oxidation, the secondary alcohol, in this case, has an oxidation number of 4 minus 4, which is 0. When we oxidize a secondary alcohol to a ketone, what is the oxidation number of a ketone as drawn? What is the oxidation number of a ketone? Yep, +2, exactly right. And you can infer that partially because when we oxidize this secondary alcohol to a ketone, we have lost an equivalent of hydride, and we'd expect our oxidation number in turn to increase by 2. Now, the reason why I think about oxidation as abstraction or removal of a hydride equivalent is because when we have a tertiary alcohol, is there an equivalent of hydride to remove? Can this tertiary alcohol, does this tertiary alcohol have any hydride equivalents that could be removed? Are there any hydrogens attached to the alcohol carbon? No, and as a result, tertiary alcohols are unreactive under oxidation conditions. There's no hydride equivalent to remove. Does that idea make sense to everyone? Any questions on oxidation numbers and which compounds are capable of undergoing oxidation reactions? So primary and secondary alcohols can undergo oxidation. Primary alcohols can be oxidized to yield aldehydes and carboxylic acids, while secondary alcohols can only be oxidized to yield ketones. Tertiary alcohols are unreactive under oxidation conditions. So, one thing that we can conclude from this study, oxidation entails the loss of hydride, H- from our central carbon. If there's no hydrogen on the central carbon, it cannot be oxidized further by removal of hydride. Does that make sense to everyone? This is another explanation for why tertiary alcohols do not undergo direct oxidation. Oxidizing agents are a little bit different than Lewis acids in terms of how they react. Any other questions on this discussion of oxidation and oxidation numbers? If not, let's keep going then. And let's discuss methods to oxidize alcohols to prepare ketones and aldehydes. It's pretty easy to oxidize an alcohol to a ketone. Pyridinium chlorochromate, also known as PCC, which is a combination of pyridine and chromium trioxide in dichloromethane, is gentle and works under non-acidic conditions. If you want to oxidize an alcohol, specifically a primary alcohol, to an aldehyde, des-Martin pyridine is a gentle and non-acidic reagent. The book mentions it's expensive, but you can make it, and it's pretty easy to make as long as you're careful. So the structure for des-Martin pyridine looks something like this. It's known as a hypervalent iodine reagent, which has an iodine in a positive oxidation state. And this iodine is a pretty strong oxidizing agent. So des-Martin periodine is useful if you want to stop at the aldehyde. It's a useful reagent to selectively oxidize primary alcohols to the corresponding aldehyde. Any questions so far? We'll discuss the mechanism for this reaction momentarily. Okay, so let's talk about the mechanism for oxidation of primary alcohols with des-Martin periodine. Des-Martin oxidation is thematically similar in terms of how you push the arrows to an E2 reaction. However, it generates a CO double bond by elimination opposed to a CC double bond. Okay, so the first step in the mechanism is our alcohol attacks our hypervalent iodine and we kick out an equivalent of acetate. From there, we have a concerted process where an equivalent of hydride is pulled off and we in turn end up donating 2 electrons into our hypervalent iodine atom. So as part of this concerted process, let's think about what we've done. First, we've formed a carbon-oxygen double bond. We have lost an equivalent of hydride. Our iodine has gained 2 electrons. The iodine is oxidizing our alcohol and the iodine atom is being reduced. And most importantly, we've lost an equivalent of acetic acid. So acetic acid is the principal byproduct in this oxidation step. So we've gone from iodine 5 to iodine 3. So des-Martin periodine oxidized our alcohol up to the aldehyde, and this is a 2 electron oxidation. So we've lost a single equivalent of hydride. Does that make sense to everyone? Any questions on the mechanism for des-Martin periodine oxidation? If not, let's look at some other reactions and their mechanisms. So let's talk about chromic acid oxidation, and let's talk about the chromic acid oxidation mechanism to prepare aldehydes and carboxylic acids. So chromium trioxide is a chromium 6 oxidizing reagent. So this is commonly done in basic aqueous solution, but it can also be run under acidic conditions. In our first step, our alcohol attacks our electrophilic chromium atom, and then base pulls off a proton to generate a neutral species. From there, base will abstract a second proton. This will allow us to form our carbon-oxygen double bond, and in turn, chromium accepts 2 electrons. So chromium is reduced in this next step. This in turn generates an aldehyde, However, compared to Des-Martin-Pyridine oxidation mechanisms, this aldehyde typically reacts further. And what we're going to show are the subsequent oxidation steps to convert this aldehyde to a carboxylic acid. Now, chromium trioxide and many other oxidizing agents principally react with nucleophilic alcohol functionalities. So if we have a nucleophile floating around, that nucleophile, such as hydroxide, can attack our electrophilic carbonyl. Aldehydes are very reactive. From there, this alkoxide intermediate can attack a second equivalent of chromium trioxide. That in turn generates the same intermediate to our first oxidation step. From there, just like before, another equivalent of base can pull off a second proton. And we'd reduce our second equivalent of chromium trioxide. That in turn gives us the corresponding carboxylic acid. So typically, if you take a primary alcohol, so if you have a primary alcohol and you subject it to oxidation with chromium trioxide and pyridine, or oxidation under any basic conditions, you will typically end up observing an appreciable amount of oxidation to the carboxylic acid. It's pretty hard to get a PCC oxidation or chromium trioxide based oxidation to stop at the aldehyde. If you want the oxidation to stop at the aldehyde, it's generally preferred to use Des-Martin-Pyridine under neutral conditions. Does that make sense to everyone? Does everyone understand the mechanism for this kind of somewhat exhaustive oxidation? We generate an alcohol via attack of a nucleophile or an equivalent of water. And then from there, our alcohol is then oxidized an additional time to give us a carboxylic acid. Does this make sense to everyone? Okay, so let's keep going then. So many common oxidizing reagents in aqueous acid will oxidize primary alcohols directly to carboxylic acids. So chromium trioxide under acidic conditions will typically oxidize up your primary alcohol to all the way to the carboxylic acid. Further, if you're dealing with a secondary alcohol, you don't have to worry about over-oxidation, right? So you can use an inexpensive reagent like sodium dichromate, which functions identically to chromium trioxide under acidic conditions. So this allows us to take a secondary alcohol and convert it to a ketone efficiently. Does this idea make sense? Does everyone see why we don't have to be as picky with our reaction conditions when we're dealing with a secondary alcohol? One other thing that I would like you to note is that the PCC, or pyridinium chlorochromate system, is typically used for sensitive alcohols at lower temperatures. So it's useful if you have a particularly reactive or sensitive alcohol and you have functional groups in your molecule that you don't want engaging in side reactions. So PCC oxidation is a little bit milder than your typical chromium trioxide oxidation. Does this make sense to everyone on the purpose of each oxidizing reagent and the mechanism for how each reagent functions? Okay, this is a good stopping point for this laboratory supplemental lecture. So we'll archive this recording.